Welcome to Middle School Mathematics Module 3, Functions and Their Graphs, for preparing for the Praxis. This is presented by TLC Tutoring Company and Arkansas State University. Let's begin with functions. A function is a mathematical way to relate inputs to outputs. What's important with a function is that every input has exactly one output. You could think of it as a machine that takes in an input and pops out an output. Another way you could think about it is mapping inputs to outputs. The way you want to see is every one has exactly one output for every input. Now, it's important to note, not all mathematical relationships are functions. A single input, if it has multiple outputs, then it's not a function. As you can see on the right, you can see that the number 2, if it's an input, can give you either 6 or 7. Because of that, it's not a function. Because if 2 was the input, how would you know whether it should be a 6 or an 8? There's no way to know, therefore, it is not a function. Now, we've seen how equations and expressions are used to perform or operate relationships with numbers. Function notation is just a formalized way to show that relationship. So a function starts with a certain input and tells you what to do to get the output. So here is a simple function. F of x equals 3x plus 4. So the letter f is the name of the function. This is function f. The variable in parentheses is the input. And the opposite side tells you what is the machine going to do? What's it going to do? So it says that you should multiply your input by 3 and then add 4 to generate the output. In functions like these, the x serves as a placeholder until you decide what you actually want to use as an input. So let's try a simple function notation example. So given that g of t is equal to 2t minus 7, what is the value of g of negative 4? So as we mentioned, the variable in the parentheses is the input. So t is the input of the function g. And this asks for g of negative 4. So we use negative 4 as the input rather than t. So we rewrite the same function, but we use negative 4 instead of t. So g of negative 4 is equal to 2 times negative 4 minus 7. Orders of operations, we multiply first. Negative 8 minus 7, negative 15. In this way, the function notation tells us that for the function g, if your input is negative 4, your output is negative 15. Now, sometimes a question will require us to use more complicated inputs compared to the last example, where our input was a single number. So let's look at this one. For the function f of x equals 3x minus 2, what is f of 2a minus b? Now, you'll notice the input x was not replaced by a number, but an entire additional expression. But the process is the same. You're going to rewrite it with, instead of x, you're going to replace that input with 2a minus b. So this becomes 3 times 2a minus b minus 2. If you distribute that out, you end up with 6a minus 3b minus 2. And that is the same function. It's the new function that you have now created. And you may see times when an entire function is used as an input, like f of g of x. That's a function within a function. So now we've talked about how to evaluate and use functions. Let's talk about graphing a function. So we've done graphing on a coordinate plane, but we can also plot functions on a coordinate plane. So function is a relationship that maps inputs to outputs, with every input gets exactly one output. So the function f of x of 2x can be graphed by selecting x values, and you find the corresponding f of x, and you plot those on the y-axis. So 0, 0, 1, 2, 2, 4, negative 1, negative 2, negative 2, negative 4. Those get me 5 points, and then I draw a straight edge, and I can see, oh, this is a line function. Now, the big thing we can use with functions is, as we said, functions have to have one input to one output. So there's a thing called the vertical line test. So what we can draw is, if you can draw a vertical line on a graph and strike the graph more than once, then it's not a function. So you have a parabola, you have an up and down line graph. Those are both functions because every vertical line I draw, I'm only going to hit the function graph once. Now these lower ones, you can see I have a horizontal parabola, I have a pivoted sine wave, and then I just have a scatter plot. But in each of these, it is possible to draw at least one, if not several, vertical lines that strike the function more than once. Therefore, they're not functions. Next, we could talk about evaluating a function. So a function can be represented by graphs or tables, and then we can use that to evaluate these functions. So let's say t of x is represented by this graph here in red, and it also is represented by the table below it. So t of 4 would be the value of the function when x equals 4. So you can look on the graph. When you go to x is equal to 4, t of x is equal to 2. Or you could look at the table and say, well, when x is 4, t of x is 2. Either way, you'll get the same answer. Now, one of the unique things about functions is they have two conditions called domain and range. So we'll start with domain. The domain of a function is all the inputs you can put into a function that gives you a real output. And remember, a real number means an actual existing number, not an imaginary number or an undefined number, a real number. So if there are any inputs are not possible, then we exclude them. So there's two cases that limit your domain. One is dividing by 0, and the other is taking the square root of a negative number. So take this example. F of x is equal to 1 over x plus 5. So looking at that, the x is in the denominator. If we set x equal to negative 5, that'll be negative 5 plus 5, and this ends up being 1 divided by 0. Well, anything being divided by 0 is undefined, so therefore it's not part of the domain. X cannot be negative 5. So for this function, we would say the domain is all real numbers except negative 5. Another case is when you take the square root or an even root of a negative number. And if you recall from that, the square root of a negative number is an imaginary number, and we're only looking at real numbers. So this equation, f of x is equal to the square root of x plus 10. So anytime the radicand, that's the value under the radical, is negative, you're going to get an imaginary number. So this has to be avoided. So looking at this one, you could say if x is ever less than negative 10, you're going to get a negative number. So we could say that the domain is all real numbers that are greater than or equal to negative 10. Or we could say x greater than or equal to negative 10. If we use the previous graph and example that we looked at, you can find the domain and range of a function without the actual equation. So looking at this, the domain would be all the possible x inputs. So we can see it goes from x equals negative 4 to x equals 4. Then we can also look at the range and say the lowest possible output is 0 and the highest possible output is 7. So the range would be 0 to 7, and the domain would be negative 4 to 4. So let's try this for a little practice. Use this information to answer some questions. So Joe had a summer job and it pays $7 an hour, and he worked between 15 and 35 hours a week. So we want to create a function to model his weekly earnings related to how many hours he worked in a week. Describe the domain and the range of this function, and in the context of your function, what does the ordered pair 126 signify? So first, let's create that function. We know we want to get earnings, so we're going to call that E. We know that he makes $7 per hour. So if I multiply 7 times the number of hours he worked, it'll tell me how much he earned. So we would say E of H, hours is the input, E is the name of the function, is equal to 7 times H. Now the domain is the range of possible inputs. Well, the input is the number of hours he works. He said he works between 15 and 35. So the domain would be 15 to 35. The range would be what's the minimum amount of money he could make or the maximum amount of money he can make. If he works 15 hours, 15 times 7 is 105. If he works 35 hours, 35 times 7 is 245. So that is the min and maximum amounts of money that Joe could earn in a week. And finally, we said the ordered pair 18, 126. Well, we have our function. 18 is the input, so this is e of 18, 7 times 18, and that is $126 with that amount of time. Now, with any function, if you have a given function, finding the x and the y intercepts serve to give important behavior information for that function. So the x-intercept is the x value that makes y equal to 0. It's where the function crosses the x-axis. Similarly, the y-intercept is the y value that makes x equal to 0, where the function crosses the y-axis. So let's try some practice here. Let's find the x and the y intercepts of this function. F of x is equal to 2x minus 2. We could simplify that and write it as y equals 2x minus 2. So to find the y-intercept, we set the x value to 0, and we find f of 0. F of 0 is 2 times 0 minus 2, so the y-intercept is negative 2. Then we do the same thing for the x-intercept. We set the f of x to 0 and rearrange to solve. So 0 equals 2x minus 2. I move the 2, I divide by 2, and the x-intercept is equal to 1. There are multiple types of function graphs, but we wanted to hit a few of the high points so that we can make sure we can identify them. So let's look at the identify how to picture a graph and see what kind of function it is, or if I give a function, then I know what the graph looks like. So let's start with a linear function. This is y equals mx plus b. That's the slope-intercept form. So for this example, y equals 1/2 x plus 2. There is one x for every y and a constant rate of change. That's m, the slope. So it's a straight line and it doesn't change. B would be the y-intercept, which we've already talked about before. A second common function is the quadratic function, which creates a parabola. The standard form here would be y equals a times x minus h squared plus k. There are two x's for every y. So like when y is equal to 4, there's 2 points on the parabola. The graph is curved because of the different rates of change. So a is the amplitude that changes the curve shape or makes it face up or down. H and k is the vertex, that's the turning point, and on this particular one it's at 0, 0. But hk would be the point that the parabola turns around and goes the other direction. An absolute value, remember absolute value is measuring how far away from 0 a number is. So it looks something like this. Absolute values are always positive, so it would look like y equals a times the absolute value of x minus h plus k. Similar to linear and quadratic with some differences. So always positive, a is still that amplitude change to move the line slope, and hk is still the vertex or the turning point where the absolute value turns around. And a simple exponential function. So exponential just means involving exponents. So y is equal to a to the x. So a needs to be greater than 0 and not equal to 1. So the exponential grows faster and faster and faster as the slope increases. So looking at this formula, a is the base value, and this will be usually a whole number, but it needs to be a real number. If a is greater than 1, the curve bends toward infinity, like the example you can see to the right here. If a is negative 1, or less than 1, the curve bends toward 0 and it will eventually go to 0. And x is the power that changes the base. Now, when we're analyzing data, we want to see what kind of function would be used to model that data. So let's just try this example. A pizza company sells a small pizza for $6 and each topping costs $2. How could we represent this data with a function? So option 1, we could represent it with a table. We could call the number of toppings x and the total cost y. So if I have 0 toppings, x, it's $6. One topping is 8, 2 is 10, 3 is 12, 4 is 14. So we can see our trends here and the way the price goes up depending on how many toppings you have. Another option we could do is we could represent it with an equation. So we know the fixed cost of the pizza is $6 even with 0 toppings, and every topping adds $2. So we could say x toppings times $2 per topping is 2 times x, or 2x. So the cost of the pizza is the fixed $6 cost plus 2 times the number of toppings, 2x. That equation will replicate the data from the table we just generated. And a third option is to represent with a graph. So we could use this table to generate ordered pairs so that when 0 toppings, it's a 6, that's our y, then 1, 8, 2, 10, 3, 12, 4, 14. Then we're going to put it on a graph. So you use the ordered pairs to make a graph that represents this data. So y, or toppings of x, is equal to 6 plus 2x. And the equation, the table, and the graph all support this as a linear type relationship. It's making a straight line, and we can see that clearly here in the graph. Congratulations for finishing Middle School Mathematics Module 3. You're done with functions and graphs, and next we're going to move to geometry, data, and measurement.